Okay, so putting everything together from what we've learned about gases with what we already know about stoichiometry, solving for a gaseous reactant is basically talking about the N in PV equals nRT. So either you're going to have like a reactant in your chemical equation that is gas, so the information you have about that gas will be like the pressure, volume, temperature, etc. So from that you can calculate the number of moles. And then using the balanced stoichiometric equation, relate moles of gas to moles of whatever other product or whatever you're interested in. And that's all stuff we already know from all the work we've done in stoichiometry. Or vice versa, you've been given information about a reactant or product that is not in the gas phase, okay? So again, starting with what you know, converting mass in grams to number of moles, use the mole ratio between that reactant or product and the gaseous one to get to the number of moles of gas. And then you're probably asked about something else from the ideal gas equation, like, hey, what volume of gas is produced? Well, you've got the number of moles because you just worked it out. You've been probably told the pressure and temperature, so you can rearrange and solve for volume. So, because Alex likes to play with our emotions, we've been asked to balance the chemical equation first. So hopefully you remember that the combustion of a hydrocarbon, like heptane, is the reaction in air with the oxygen in the air, which will burn. And if it's a hydrocarbon, the only possible products are carbon dioxide and water. And the smart way to balance this without crying salty, salty tears is to balance carbon first, then hydrogen, then oxygen, just with whatever's left. So we've got 7 carbons in the equation, so boom, I'm going to do that. We've got 16 hydrogens, but it's H2 in the water, so I just need half of 16, which is 8. Okay, so my hydrogens are balanced. So then I'm just going to have a quick tot up of how many oxygens I have over here. So 7 times 2 is 14, plus 8 is 22 oxygens on the right-hand side, but it is O2, so it's going to be 22 divided by 2. Now, if you've got an even number here, this is great, right? Because 22 divided by 2 I can do, that's 11. If I did not have an even number there, I'd have to like multiply the whole equation by 2 to get rid of that divided by 2. So now we have a balanced chemical equation. So what are we asked to compare? Mass of heptane, and we want a volume of carbon dioxide. So the reactant we're interested in is the heptane. There's 1 mole of that. Every 1 mole of that burns makes 7 moles of carbon dioxide. So whenever you're asked for any stoichiometry question, I always think it's smart to write the mole ratio of the thing that you have information about and the thing you're interested in as an equivalency. So for every 1 mole of heptane, you will form 7 moles of carbon dioxide. That way you can always make sure you get it the right way up when you're doing your stoichiometric calculation. So we've nastily been given our mass of heptane in kilograms, so we're going to have to convert that into grams. We've got the pressure, okay, it's 1 atmosphere. We've got the temperature, but it's only in degrees Celsius. So as always, for any gas law stuff, we've got to convert to Kelvin. So 273.15 plus 14 is going to give me 287.15 Kelvin. That is my temperature. R is going to be the gas constant. So my PV equals nRT. I'm going to want to rearrange and solve for volume. So it's going to be N, the number of moles of carbon dioxide, times R times T over the pressure. Okay, so I've got to work out my number of moles of carbon dioxide. So I'm going to go from the mass of heptane, C7H16 in kilograms. I got to convert that to the mass, whoopsie, of heptane in grams before I can do anything. And then if I got the mass of heptane in grams, I can use the molar mass of heptane to get to the number of moles of heptane. C7H16, and then if I have that, I've got a balanced chemical equation. I've just written my mole ratio so I can get to my number of moles of the carbon dioxide, and then we're going to use the ideal gas equation to get to my volume of carbon dioxide. Okay, so my conversion between kilograms and grams is 1 kilogram is 10 to the power of 3 grams. My conversion between mass and moles of heptane is 1 mole of heptane has a mass of, what's the molar mass? Let's do it quickly. 7 times 12.011 plus 16 times 1.0079, I think. Can't remember. It's about 100. If I'm off, so be it. 100.2034 grams. Okay. And then we've already got our mole fraction between heptane and carbon dioxide here. And we've already got our rearranged value of the ideal gas equation here. So we're just going to multiply by RT over P. All right, so our mass was 0.220 kgs. So 1 kg is 10 to the power of 3 grams. And then we're going to divide through by a molar mass to convert grams to moles. So the molar mass was 100.2034, probably. So every 1 mole of heptane weighs that much. So this is like the magic key right now for any stoichiometry problem, which I think is so important. Like, I'm just going to use dimensional analysis. I don't want C7H16. I don't want the heptane. I want to know about my number of moles of carbon dioxide. So notice how I have not put the numbers in because I've already written them up here. They're directly from my balanced chemical equation, but I just want to make sure I get the actual species the right way round before I worry about numbers, okay? Because sometimes people are like, oh, you just got to times by 7 or just divide by 7. Well, that's a 50-50 coin flip, and we don't like to get things wrong, okay? So, yes, this time you do times by 7, but, you know, just if you check your units, you'll know, okay? So then we've got moles of carbon dioxide, okay? So now that is going to be my N in my PV equals nRT. So I'm just going to times by my RT over P, or you could like press equals and actually have the number of moles and do it on another line, up to you, right? You know what, I'll do it that way just so it's a little bit more transparent. So 0.220 kilograms times 10 to the power of 3, okay, divided by 100.2034 times 7 is going to give me my moles of carbon dioxide. So check the dimensional analysis if you don't believe me. Okay, so moles of hexane have cancelled. We got moles of carbon dioxide, and I've got that's 15.36873 blah 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 4. Okay, that'll do. Okay, so now we just have to stick that in the ideal gas equation to get our volume. So my volume is my number of moles of CO2, so 15.236874 moles of carbon dioxide times the gas constant, eta atmospheres per mole per Kelvin, times, oh my goodness, the temperature, which I did calculate, 287.15 Kelvin divided by what is the pressure? Where is it? 1 atmosphere. That's a little bit anticlimactic, I'm not going to lie. Okay, so what do we have? 15 point... Hang on, I didn't even write that down. It's 15.3687. 3687. There's no 2 in there. Where did that 2 even come from? Let's just cross out the 2. That's probably going to be the easiest way to fix that. I don't know. I must have hit the button at the same time as I was typing the 3. Okay, so 15.3687 times 0.08206 times 287.15 divided by 1 is 362 litres. All right, that's a lot of carbon dioxide.